Product and quotient rule. The product rule. If f and g are differentiable, then f times g is differentiable, and we have the product rule, which says the derivative of f times g is equal to f of x times g prime of x plus g of x times f prime of x. Essentially, we leave f of x alone, multiply by the derivative of g, then we leave g of x alone and multiply by the derivative of f, and we add those two together. Another way to help think about this is we can take the first function, leave it alone, times the derivative of the second, plus the second function, leave it alone, times the derivative of the first. So the big warning here is that f times g prime, if we take the derivative of f times g, it is not simply just take the derivative of f and take the derivative of g. So I can't take the derivative of each one separately of a product. I have to apply this product rule. Let's take a look at some examples. Find f prime of x given f of x equals x squared plus 1 times e to the x. So I do have a product, x squared plus 1 times e to the x. And sometimes what students think to do is distribute in the e to the x, but I would still have a product. I would still have x squared times e to the x. So the product rule on this example is unavoidable. So we're going to go ahead and find f prime of x, which is equal to the first function, x squared plus 1, and then the derivative of the second, plus the second function, e to the x, times the derivative of the first function, x squared plus 1. So I am taking the time to write everything out, at least for the first example, because eventually what we want to do is head straight to this second line here. So x squared plus 1 and the derivative of e to the x, well, that's just e to the x, so I've actually taken the derivative on this part, plus e to the x, that first function, here on the second part, and then the derivative of x squared plus 1 by the power rule is simply 2x. So this is officially the derivative, but we're going to go ahead and now simplify it as much as we can. So we have e to the x in common in both, so I can factor out e to the x, and I'd have an x squared plus 1 left from the first term, and I'll have a plus 2x left in the second term. And I can actually go a little bit further than this, so x squared plus 2x plus 1 actually factors to x plus 1 squared. It's a perfect square trinomial. So this is the most simplified answer here. So really from these two steps, this is simplification. This is the part that's new, the product rule. So we had a function of x times a function of x, so I had to apply the product rule in this example. We'll go ahead and look at the second example now. Find the derivative with respect to x of a product x times g of x. So in this example, I have one specific function, the function x, and then one generic function, which we're just calling g of x. So here, when I attempt to find the derivative, I'm going to go straight to the answer here. So it's going to be the first function, x, and then the derivative of g of x. Well, g of x is a generic function, so the best I can do is write prime notation here, g prime of x, plus the second function is g of x, and then times the derivative of the first function. Well, the derivative of x is just 1. So x g prime of x plus g of x is actually the derivative, and it's the best that we can do. There's no simplifying. I can't factor out anything because these aren't the same function. One's a derivative, one's the original. And now we move on to the quotient rule. If f and g are differentiable functions, then f over g is differentiable for all x as long as g of x does not equal 0. The denominator can't be 0. And the derivative is found by using this quotient rule, which looks pretty intimidating. It says that the derivative is g of x, that's the bottom function, times f prime of x, the derivative of the top, minus f of x times g prime of x, all over g of x, the denominator, squared. So this is the formal way of writing it. I have a little informal way that might be kind of helpful in terms of remembering this formula. So if I call the top function the high function and the bottom function the low function, and I want its derivative, so prime notation is here, then the way that I've been taught to remember it, and I still think about it like this when I apply it, is low d high minus high d low over low squared. So I'm not totally sure if it's helpful, but if it is, then definitely go ahead and apply it. It is something that I will be saying when I apply the quotient rule, low d high minus high d low over low squared. I encourage you to repeat it a couple of times and it'll stick. But the bottom line is, the big warning here is if I have a quotient and I try to take its derivative, I cannot simply take the derivative of the numerator and take the derivative of the denominator. That doesn't work. I have to apply this quotient rule. Example time. Find the derivative of each of the following using the quotient rule. So we'll start here. The derivative with respect to x of x minus 1 all over 2x squared plus 3. So I have a quotient of two different functions here. They're both polynomials, so we'll jump straight into the quotient rule. And on this example, I will go ahead and write everything out. So it's low, the bottom function, so 2x squared plus 3, d high, so the derivative of x minus 1, so low d high minus high x minus 1, d low, the derivative of the bottom, derivative of 2x squared plus 3, all over the bottom squared, 2x squared plus 3 squared. So I actually haven't taken these derivatives yet, so I need to go ahead and move on with that process. And again, that would be a goal to just go straight to this answer that we're about to write down right now. You don't have to do this first step. So I'm going to go ahead and write 2x squared plus 3. And now the derivative of x minus 1 is just 1. So this is times 1 minus x minus 1. Notice that I'm keeping all binomials in parentheses. That's important. And then the derivative of 2x squared plus 3 is just 4x. And then all over 2x squared plus 3 squared. So this is actually the derivative. From here, it's going to be simplification. And I want to talk about some common mistakes. At this point, a lot of students want to cancel out 2x squared plus 3 and a 2x squared plus 3 copy. I can't do that. They're not factors. So on the top, I'd have to have multiplication, just two things being multiplied. I can't have a sum or difference at all. So the fact that this subtraction sign is here means that I cannot cancel this 2x squared plus 3. So on the numerator, I could try to find a common term that factors. There's nothing that factors out of each term here. So I'm just going to go ahead and multiply out 2x squared plus 3 on the left minus the 4x would distribute and the minus would distribute. So I'm going to do both at one time. So it's going to be minus 4x squared and then plus 4x all over 2x squared plus 3 squared. And combining like terms here, I have negative 2x squared plus 4x plus 3, and then all over 2x squared plus 3 squared. And what we do at this point is we would check whether or not the numerator factors, because if it factored, then we'd want to simplify by factoring completely and then potentially canceling with something in the denominator depending on what the problem looks like. But in this example, the numerator does not factor, so we are going to go ahead and leave our answer like this. Moving on, in this example, take the derivative with respect to x of 3x minus 1 all over x times e to the x. So on this problem, I actually have both a quotient and a product. So the denominator was x times e to the x, and it's really helpful to say out loud, or at the very least think about reading the function as you see it to figure out what rules you're going to need to differentiate it. So here it's a quotient and a product. And sometimes what students want to do is go straight for the product and apply the product rule. But if you apply the product rule, then you're assuming we can take the derivative of the numerator and denominator separately, which we cannot. So on this example, I have to go for the quotient rule first, and within the quotient rule, perform the product rule. So let's see what that looks like. We're going to go ahead and start with the quotient rule, which is low d high. So low is the entire bottom product, x times e to the x, low d high. So the derivative of the numerator, 3x minus 1, is 3. Minus high, the numerator, now it's a binomial, I'm going to keep it in parentheses, d low. So the derivative of x e to the x is what goes next. So I'm going to go ahead and put a big set of brackets here, because we're going to have to take the derivative of x e to the x. So I'll just go ahead and kind of write that above here, the derivative with respect to x of x e to the x. So let's go ahead and focus on that part. We're going to go ahead and do the product rule, which is we have to take one function, leave it alone, multiply it by the derivative of the second one. So we have first d second, well, the derivative of e to the x is e to the x, plus the second function, e to the x, times the derivative of the first. The derivative of x is just 1. So that was d low, the derivative of the denominator. Now I can't now forget to go back into the quotient rule, because this is all over low squared. So x e to the x squared. So I'm going to erase this top part here. So here, this is the derivative. It was the quotient rule, low d high minus high d low, all over low squared. But my d low, the derivative of the denominator, required a product rule. And from here, we would try to see if there's any simplifying we can do, and there is some simplification. So in the first term, I'm going to go ahead and put 3x e to the x to see a little more clearly, minus, we have 3x minus 1. Inside here, I can factor out an e to the x. So there's an e to the x in common in both, so I have e to the x, and then I would have an x plus 1 left over. So I have x plus 1. And then let's see, all over the denominator is x e to the x squared. And I can go a little bit further. So now I have two terms. This is all one term, and this is all one term over here, right? Terms are separated by addition or subtraction. And I can factor out an e to the x. So I'll factor out an e to the x, and I have 3x minus 3x minus 1 times x plus 1, and then all over, in the denominator here, I'm going to think about this as, let's see, it's x squared, and then I have e to the x squared. So I can write that as e to the 2x, but I'm going to write it as e to the x actually instead. Because I can cancel one of those e to the x's with the one I factored out of the numerator. So from here, let's see what's left. Let's see what else we can do. Alright, so we have 3x, and then minus, we would go ahead and distribute this out. So we have 3x minus, we have 3x squared plus 2x minus 1. All over x squared e to the x, and then we can go ahead and distribute in the negative into all three terms and combine like terms. So we'd end up with negative 3x squared plus x plus 1 all over x squared e to the x. And that's the best I can do. The numerator doesn't factor, so there's no potential for canceling anything in the numerator and denominator anymore. So here was my derivative, and then the rest was simplification. So you're going to notice that we do a lot of factoring out whenever I have two or more terms. So we factored out an e to the x at this step, and then we factored out an e to the x on the next step. And we'll see more of these types of. In these next examples, we're asked to rewrite each of the following so that the power rule can be used instead of the product or quotient rule. So find the derivative of f of x, where I can see the way that it's set up, it's a product, x squared plus 1, and then times 2 over x minus x. But in this example, if I distribute out, then I would have a sum or difference of terms that I can apply the power rule to. So I don't just want to necessarily go for what I see automatically, like I see a product, do the product rule, if I can do some other algebra that allows me to avoid that process. So here, if I go ahead and multiply this out, this would be equal to, let's see, I have 2x squared over x, and then minus x cubed, so I'm doing first outer, and then inner, plus 2 over x minus x. And I'm going to simplify a little bit further. So I have 2x, because I did cancel out, right, an x and one of the x's in the numerator, and then minus x cubed. In order to apply the power rule to 2 over x, I don't want to think about that as a quotient. I mean, I can, but it's way too much work to think about this as a quotient. Instead, I want to rewrite this as 2x to the negative 1. So remember, this is x to the first power, so I can move it to the numerator and make it a negative exponent, and then minus x. So now I have simplified my original function. Now I can take the derivative using the power rule. So now I can find f prime of x, and I want us to be careful about our equalities. So here I wouldn't just want to write equals and then take the derivative because the original function isn't equal to the derivative. So notice I started f prime of x now is equal to, and I'm going to take the derivative of each piece here. Actually, I'm going to do a little bit more simplifying first. So the 2x and the minus x can combine. So I'd have just x minus x cubed plus 2x to the negative 1. To avoid having to simplify my derivative, I just simplified the original function a little further. So I end up with 1, the derivative of x, minus 3x squared, so using the power rule on x cubed. And then here, bring the negative 1 to the front, I get negative 2x. And if I subtract 1, I get to the negative 2. So this is my derivative without applying the product rule. In this example, we're going to do some rewriting so that we can avoid the quotient rule. So here, the indication that I'm going to try to avoid the quotient rule is when I have a quotient where there's only one term in the denominator. That's what indicates that I'm going to try to use some algebra first. And I'm going to rewrite this denominator as 2x to the 1/3 instead of the radical notation. And the whole idea behind the one term on the bottom being helpful is that it allows us to split up the fraction. So we're going to take the derivative instead of 4x squared over 2x to the 1/3 plus 3x over 2x to the 1/3. So I've turned this into a sum of two different terms now. And I can simplify each one of these terms and just use the power rule on it. So here, to simplify each of these terms, I can reduce the coefficients in front, at least on this first one. To reduce the variables, remember I subtract the bottom exponent from the top exponent. So I'd be subtracting 1/3 from 2 here. So I'd end up with the derivative of 4 over 2 is 2, and I'd end up with x to the 5/3. I'm subtracting 1/3 from 2. And then plus, the coefficients here don't reduce, so I have 3/2 x to the 2/3. So on this example, I would be subtracting 1/3 from 1, which gives me 2/3. So now, the power rule works for each of these individual terms. So the power rule says here, I'm going to go ahead and multiply the exponent 5/3 times the coefficient in front, so bring it to the front and multiply. I have 10/3 x to the 2/3. I'm subtracting 1 from the exponent, subtracting 3 over 3. Notice I dropped the d dx because I'm taking the derivative already in this step with respect to x. Plus, here, if I multiply 3/2 times 2/3, I actually just get 1. So I'd have 1x to the negative 1/3. Derivatives of trigonometric functions. Well, here they are, the derivatives of the trigonometric functions. So the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of secant is secant tangent. The derivative of cosecant is negative cosecant cotangent. The derivative of tangent is secant secant, or secant squared. And the derivative of cotangent is negative cosecant cosecant, or negative cosecant squared. So there are a couple of things I want you to recognize that will help you remember these. Let's start with the fact that all the derivatives of the trig functions that start with cosine, cosecant, and cotangent, so these right three derivatives, are all negative, right? They are all negative. So that's one helpful thing to remember. All the derivatives of the ones that start with co are negative. And then there's another little technique that actually a former student recognized and shared with me. I thought it's a great way to help remember these. So let's focus over here on the derivative of secant and the derivative of tangent. So what helped them remember this derivative is that the derivative of secant, secant tangent, there's 2 copies of secant involved and 1 copy of tangent. And the derivative of tangent has 1 copy of tangent and 2 copies of secant. So they said that it helped them remember that secant and tangent went together. There's always 2 copies of secant and 1 copy of tangent. And the same applies, if we look over here, for cosecant and cotangent. So cosecant x's derivative has a cosecant and a cotangent, so 2 cosecants, 1 cotangent. And the derivative of cotangent has 2 cosecants in it. And then you just have to remember the negative part. So might be helpful, hopefully, to help you remember the derivatives of the trig function. Let's go ahead and do an example. I'll start to combine a couple of rules here. So the derivative of 2 cotangent x plus 6e to the x times secant x. So I'm going to go ahead and take the derivative of each one separately since they're added together. So the derivative, I'm going to work down, the derivative of 2 cotangent x. So the derivative of cotangent was negative cosecant squared, so I'm going to keep the negative in the front. So negative 2 cosecant squared x plus, now I can take the derivative of the second piece separately, but this requires a product rule. So I have 6e to the x is the first function, and secant x is the second function. So I have the first function, 6e to the x, times the derivative of the second function. The derivative of secant is secant x tangent x. So that's first function, derivative of the second, plus the second function, secant x, times the derivative of the first. Well, the derivative of 6e to the x is just 6e to the x. And on this problem, there's not really a whole lot that I can do to simplify. The only thing I could do is take out, let's see, a 2 in common from everything. I won't bother doing that. I'll just rewrite it a little bit nicer. Negative 2 cosecant squared plus 6e to the x secant x tangent x. And I'll put the 6e to the x in front here. 6e to the x secant x. So this big thing is my answer. Here, take the derivative with respect to y of sine y plus cosine y all over 3y squared minus 2 tangent y. So we apply the quotient rule. We have low d high, so 3y squared minus 2 tangent y times the derivative of the numerator. So derivative of sine is cosine y. Derivative of cosine is negative sine y. Low d high minus high sine y plus cosine y. D low. The derivative of the denominator is 6y minus 2 secant squared y. and then all over low squared, so 3y squared minus 2 tangent y all squared. And we will not attempt to simplify this answer. In this example, we're asked to find the second derivative of y equals x squared times cosine x. So we are going to need to use the product rule. X squared is one function times cosine x is another function of x. So we'll start with the first derivative here, y prime. So it is the first function x squared times the derivative of the second function, the derivative of cosine, is negative sine x, have to use parentheses or it'll look like subtraction, plus the second function cosine x times the derivative of the first, the derivative of x squared, is 2x. So here we'll do a little bit of rewriting, make it look a little nicer. I have negative x squared sine x, and then plus 2x cosine x. And it's worth it to try to simplify a little further to see if that might help us for the second derivative. So in common in both of these is an x, so I can factor out an x, and I'd be left with negative x sine x plus 2 cosine x. But that simplification doesn't really help me. I still have to do a product rule here, and then a second product rule inside of that one. But looking at this version right here, where we left off, I'm going to have to use two product rules to find the second derivative. I have negative x squared times sine x, 2x times cosine x. So this one's going to be pretty long. I'm going to have y double prime, we'll start it over here. We're going to use the product rule on this first piece. So the first function, negative x squared, times the derivative of sine is cosine x, plus the second function is sine x, times the derivative of the first is negative 2x. So this right here is just the derivative of negative x squared sine x. And then we'll do plus, apply the product rule to this piece, the first function 2x, the derivative of cosine is negative sine, and then we have plus the second function cosine x times the derivative of the first 2. So now let's see if there is any simplifying to be done. Let's just clean up each term first. So negative x squared cosine x minus 2x sine x minus 2x sine x. We can do a little bit of simplifying. Plus 2 cosine x. So we can combine some like terms here. So these two terms in the middle are like terms. So we can write our final answer as negative x squared cosine x minus 4x sine x plus 2 cosine x. So that's a lot of product rule practice. So here are the derivatives of the inverse trig functions, and they're not really pretty. So if I look at the derivative of sine inverse of x, it's equal to 1 over the square root of 1 minus x squared. And the derivative of cosine inverse of x is negative 1 over the square root of 1 minus x squared. So I still have the fact that the derivative of this inverse function that starts with a co is negative. The derivative of tan inverse is 1 over 1 plus x squared. And the derivative of cotangent inverse x is negative 1 over 1 plus x squared. So again, those that start with co on the inverse trig functions are negative. And then we have secant inverse x's derivative. It's 1 over the absolute value of x, and then the square root of x squared minus 1. And cosecant is the same, only negative. So just a quick notation review, sine inverse of x is equivalent to the notation arc sine of x. And the same thing applies for the other trig functions. Cosine inverse is equivalent to arc cosine x. So we have to be comfortable interchanging those notations. So let's take a look at this one example. I have the derivative of this product x times sine inverse of x. So we'll have the first function x times the derivative of sine inverse, as we just looked at, was 1 over the square root of 1 minus x squared. And then we have plus the second function, sine inverse of x, times the derivative of the first. Well, the derivative of x is just 1. So there's not much I can do here. I'm just going to go ahead and put the x in the numerator. I have x over 1 minus x squared plus sine inverse of x as my derivative. And here we have the derivatives of exponential and logarithmic functions. So over off to the left, the derivative of the exponential function, the derivative with respect to x of e to the x is e to the x. But let's generalize this. So let's say we want to know the derivative of a general exponential function, which looks like the derivative with respect to x of b to the x, where let's remember that the base has to be positive. In that case, the derivative is natural log of the base times b to the x. And we can see that the derivative of e to the x, being e to the x, still falls into this derivative of a general exponential function rule, because if I attempt to take the derivative of e to the x using this rule, then I end up with natural log of the base times e to the x. But we know that natural log of e is just 1. So that's why the derivative of e to the x is just e to the x, because it's really just falling into this category of a general exponential where the base is e. And then let's talk about the inverse of exponential functions, which is logarithms. We'll start with the derivative of the natural logarithm. So the derivative of natural log of x is 1 over x. And that's when x is greater than 0, when x is positive. The derivative with respect to x of the natural log of the absolute value of x is also 1 over x, and that's for x not equal to 0. So now this includes being able to plug in negative numbers, because the absolute value bars take care of that. We can't normally plug negatives into natural log. And positive numbers, but we still can't plug in 0 because there's a vertical asymptote on the graph of natural log x at 0. And then we'll generalize this, the derivative of a general logarithm. So if we have the derivative of log base b of x, it ends up being 1 over x, and then multiplied by that x in the denominator is natural log of the base, natural log of the base. And again, this only applies when x is positive, because for logarithms, you can only plug in positive numbers. And just to kind of show, just like the last one, that the derivative of the natural log of x is really just a special case of the general logarithm, let's remember that on a natural log function, the base is e. And so here, if I have the natural log of e, that's just 1, which is why the derivative of natural log x is just 1 over x. So this general logarithm, still applies to natural log of x. We just don't bother putting natural log of e because that's just 1. Let's go ahead and take a look at an example. We want to differentiate x cubed times log base 4 of x. So differentiate, of course, means find the derivative. So I'm going to go ahead and switch to d dx instead of differentiate. So the derivative with respect to x of x cubed times log base 4 of x is going to require the product rule. So I'm going to go ahead and leave the first function alone, x cubed, times the derivative of the second function. Well, we just learned the derivative of a general logarithm with a base of 4 is going to be 1 over x, and then we need to multiply by natural log of the base. So on this example, the base is 4. So that's leaving one function alone times the derivative of the other function of x, And then the rest of the product rule says, now do the opposite. So we're going to go ahead and leave the second function alone, log base 4 of x, times the derivative of that first function. The derivative of x cubed is 3x squared. And I won't really do a lot of simplifying here. I can cancel out this x and one of these x's, so this would be x squared. So I'm just going to go ahead and leave my answer as x squared over natural log of 4, and then plus 3x squared times log base 4 of x. In this example, we have the derivative with respect to x of x times 3 to the x all over natural log of x. And so in the numerator, I have a product of two functions of x. I have x times 3 to the x, and then I also have a quotient, so divided by natural log of x. So I'm going to need both the product rule and the quotient rule. But I am going to have to start with the quotient rule. So I can't just jump into the product rule, because then I would be taking the derivative of this numerator here, which ignores the fact that this is a quotient of two functions of x, and therefore I need to use the quotient rule. So the quotient rule says we're going to start with the bottom function and leave it alone. So lo, the bottom function is natural log x, times the derivative of the numerator. So that's going to require a product rule. So I'm going to go ahead and use a set of brackets here. So what's going to have to go in this set of brackets is the derivative of x times 3 to the x. So I'm just kind of doing that so we can just focus on that piece. So the derivative of this product is going to be, we leave one function alone. I'm going to leave the first function alone. So that's x times the derivative of the second function. Well, this is a general exponential. The base is 3. So we're going to have a natural log of 3, natural log of the base, times 3 to the x. So I've left the first function alone, times the derivative of the second function, and then plus, we leave the second function alone, so we're going to put 3 to the x, and then times the derivative of the first function, which is just going to be a 1, so times 1. So we have lo, the bottom function, times the derivative of the top, d high, and then we're going to go back into the quotient rule, so we're going to have minus high, the top function, so that's x times 3 to the x, d low. So what's going to come next right here is I'm going to have the derivative of natural log of x, which is just 1 over x. So I have low, d high, but the derivative of the top was a product rule, minus high, the top function, d low, the derivative of the bottom was 1 over x. And then all over the bottom squared, so all over the natural log of x squared. I'm going to go ahead and make this blue, just to show that that's the derivative part. All right, so this is my derivative. In terms of simplifying, what kind of simplifying can I do to this? Let's see, so this x here, this is all multiplied. So even though there's a bracket, right, brackets and parentheses both mean multiplication, multiplication here. So this is an x and then times a 1 over x. So let's just go ahead and cancel those out. And then let's see, what else can I kind of think about doing here? So this natural log x and this, one of these natural log x does not cancel, because this is all one big term here, and then this is all one term here. So I want to be careful about that. The only thing I could see to do is pull out a 3 to the x. So I'm going to do this in 2 steps to help us see it a little bit clearer. So inside the brackets, there are 2 terms. So this whole thing, x times natural log 3 times 3 to the x, that's all one term, plus 3 to the x times 1, that's all one term. So what's in common between these two is a 3 to the x. So what I'm going to do is pull that out. So I have a natural log x here. I'm going to take out a 3 to the x, and then what's left is x natural log 3 plus 1. All right, and then over here, the only thing left is a 3 to the x. So minus 3 to the x over natural log of x squared. Okay, so now this is all one term. Let's see if I can switch some colors here. All of this is one term, and then this is one term. So they're separated by subtraction, so we can look at them as one term and one term. So what do they each have in common as a factor? They both have a 3 to the x in common. So that's what I'm going to go ahead and pull out next, is this 3 to the x. So if I factor out a 3 to the x, then I'm left with natural log x times x, natural log of 3 plus 1, and then minus 1, all over natural log of x, quantity squared. And is there anything else really that I can do that's sort of interesting here? Not really. I mean, this natural log of x would technically distribute. So this natural log of x right here would distribute to these two terms. But there's not going to be any like terms in there to combine. But let's just go ahead and do that for the practice. So we have 3 to the x times, let's talk about it. So natural log of x times natural log 3. There's really no like combining we can do necessarily. We're just writing them all next to each other. So a common mistake is that sometimes people multiply this x, and I can't do that. So natural log x is kind of stuck, right, as its own function. X is stuck and natural log 3 is stuck. So we're going to really just leave our answer as x natural log x times natural log 3. All I did was sort of rearrange the order. Then natural log x distributes to the 1, so plus natural log x, and then minus 1, this one that was just hanging out in the back, over natural log of x squared. And that's it. There's not really anything else that I can do to this function. It's just kind of ugly.